Thank you. Um, Also, very thanks for giving me this opportunity to talk about my previous work on surface reconstruction. So, as Dee might have introduced, my name is Jiahui Huang, and currently I've already joined NVIDIA. I have become a research scientist in NVIDIA. I'm currently located in Beijing. So, I mean, if you're at Beijing, welcome to visit the office. So previously, I graduated from Tsinghua University, supervised by Professor Shimi. And today, it's a great honor of me to introduce our recent work on surface reconstruction. So specifically, I'm going to talk about the solver frameworks for tackling the problem of surface reconstruction. So it might be a little bit different from the mainstream work where, a simple neural network is applied to solve this problem. So let's get started. The problem of surface reconstruction is about to given an input point cloud, this point cloud may be partial or it could be occluded, and there could also be a lot of noise from this point cloud. And what we want to do is to reconstruct an output mesh, which means that we want a triangular mesh from it so that we could visualize it. There could be many applications such as visualization, just like novel view synthesis, and also we could do simulations on this meshes, and also it's all about 3D world democratization or digitalization. So you would be able to estimate these like intrinsics of the scene or do shadow estimation and all this stuff. So in this traditional point of view, given an input point cloud, which might be noisy, partial, or even large scale, there could be millions of points in your input. And a very traditional approach is called Poisson surface reconstruction, which is published in 2013 by Michael Kochton. And so in this work, the basic problems, the method to tackle this problem is actually a linear solve. The final problem here is actually solving a Poisson equation, as you can see here. So given an oriented points, what you want to do is to construct an indicator field so that the gradient of this indicator function is equivalent to the oriented directional field. As a result, it could really reconstruct highly accurate points, but only if the input points is kind of smooth. So it really assumes that you have pretty good quality points, and it could not complete missing regions from the input. While on the other hand, if you look at all of the works, the recent 5 or 6 years, we have, for example, a seminal work called convolution occupancy networks by Song-Yu from in 2020. What it does is that it just constructs a feed-forward network, which means that given a point cloud, you feed it forward. You just input, you feed it into a neural network, and this network is going to give you this occupancy prediction from which you could extract meshes. So actually, an illustration is shown here. But also recently we have another work called Circle, which kind of make this entire deep learning framework large scale by using sparse convolution and sparse operations on the network, so it could reconstruct really large scale scenes. So here's a result. We could reconstruct like this large scale meshes. Just feel free to interrupt me anytime if I made any mistakes or you have anything that you don't understand. But one thing that we actually find from this work, or actually all of the previous neural network-based feed-forward type of work, is that neural network, if you just directly wanted to infer like a surface, it's not very good at it. It is not very good at solving precise problem, which means that the reconstructed surface, if you really wanted to fit into the input point cloud very well, it's actually it's not an expert at it. But on the other hand, if you think about the SPSR work that we mentioned earlier, the Poisson reconstruction work earlier, because of the solver that is used, you could actually by minimizing the energy function, you are somehow guaranteed to reach the local minima of that energy, and such that your surface could fit your input point cloud quite well. So if you summarize it in the 3D space, for example, given a noisy input point cloud of a chair, you could for Poisson surface reconstruction, you could only get this noisy or overfitted result, and for this neural network based thing, you more or less get underfitted results. So the solver framework that I'm mainly gonna talk about today in this very short talk is all about combining these two different approaches. So mainly we want to borrow to marry the benefits of the two worlds. So if we could actually combine the linear solver or energy minimization problem with some priors learned from neural networks, we could actually combine the benefits of both worlds by leveraging the low-level data constraints from the solver, while also enabling high-level semantic modeling from neural network or from large-scale data. So this is essentially the goal. So the key design problems here is that, because we want to combine learning and solving scheme, so the problem is obviously there are actually three key problems here. So the first one is what to learn and what to solve. Like how do you basically combine the features from these two worlds? And then what kind of 3D representation you want to use. And thirdly, once you've constructed an energy minimization problem, how to solve it efficiently so that it could reach something reach a similar performance as these standard feed-forward type of neural network. Hence, in today's talk, I just want to give two basic examples under this framework. Of course, this is a large framework, but I just want to give you two examples, two exemplar work that I did previously, so that you guys could be really familiarized with what exactly this is doing. So the first work is called A Neural Galaxy Solver for Accurate Surface Reconstruction. So this is already published in Seagar Fisher 2022 from the group of friends in Tsinghua University. So the background of this work is really we try to incorporate learned priors into the screened Poisson surface reconstruction work. Just to recap, the goal of screened Poisson reconstruction, or I just wrote SPSR here, is to reconstruct an dense indicator field from an oriented point cloud, which is shown here in this cloud, in this cowl image. And the final energy function that we would love to solve is actually a combination of normal constraints and positional constraints. In the normal constraints, we want the gradient of the function to be equivalent to the normal, while for positional constraints, we really want the final implicit function that we evaluate to be equal to some predefined values at the point of input. In order to actually solve, or actually, because this is a functional problem, it's like a variational problem where the best solution is actually a continuous function. To effectively discretize it, we use this finite element approach by decomposing the original function into multiple levels plus multiple basis functions, which I'll show later. And then in that way, we could actually discretize the entire functional problem into a closed form linear solver, which is a closed form minimizer. So how does this finite element discretization work? Actually, it's quite easy. So the target implicit function, or f here, is discretized, or is factorized as a combination of functions across a range of level of details. So if you look at the gray functions here, it's actually the addition of these different functions that comes from different frequencies. They have fixed shape, which is like this bell-shaped thing. but they have varying scales and, of course, varying frequency. So what we do in this work is actually to improve, or actually to make this entire framework more flexible by introducing learnable basis functions, meaning that all of these small functions, like this blue, purple, red, or yellow small functions, could be actually learned. So how did we do that? So what we do is that we parameterize the basis as a summation of elementary functions. So the implicit function is a summation of basis functions, and the basis function, each of the basis function is a summation of elementary functions, which is very simple. We could, utilize this very simple elementary functions, x squared, x cubic, or x to the power of p, plus the sinusoidal functions, or trigonometric functions like sine or cosine functions. We combine these very basic elementary functions with a learned coefficients, meaning that actually these coefficients are learned, or actually are predicted by some other, like neural networks or whatever, and then we could actually combine them and form various different kinds of basis functions, like what is shown on the top right corner. As you can see, so the very naive basis function that is used in the Poisson surface reconstruction work is actually this ball-shaped function. And by using these learned basis functions, if you incorporate learnable coefficients into these basis functions, you could essentially get these different shapes, or these different basis functions, which have various different shapes. And in a very simple overfitting experiment, we found that using the very naive, we call it Bézier tensor basis, or the default basis function using SPSR, we could only get these very blurry reconstructions like this. But if you could actually let your basis function also to vary, if it is also flexible, you could obtain like a geometry of much higher details than the left one. Is there any problem here up to this point?
Excuse me. So the question is how to get those learnable bases.
Oh yeah, exactly. So there's learnable basis, learnable. So actually there are two coefficients here. So first one is this learn coefficients. Learned coefficients are actually predicted by the network, which I will introduce later. So we haven't actually touched this part, by the way. The other coefficient is actually these alphas. So the entire implicit function that we want to extract measures from is composed of basis functions, and each of the basis functions have a different scale, which we denoted as alpha here. So this alpha here could actually be directly solved from a linear system, which is this L alpha equals D. So this is just a very simple linear solve that you could directly use. And the construction of the linear system is actually also not that hard. It's just, you could just construct each of the term here by utilizing the Euler-Lagrangian theorem, and then you could discretize the original function problem where there are integrals and also some discrete summations, and you could all transform these into a very like closed form solution. So given this alpha, L alpha equals D, you could construct these left-hand side and right-hand side in a very efficient manner, because your basis function is just a summation of elementary functions, and the integral over these elementary functions could be pre-computed. So all you need to do is to incorporate the learned coefficients, which is here, which is inferred by neural network, which I will introduce later, but it's actually quite easy, just a linear combination of different integrals. So it's actually quite easy to build. So the entire framework goes like this. So given an input point cloud, we first of all, like we pass it through a adaptive sparse convolutional network. So this is just like a traditional UNet, but this UNet is more or less sparse because your input points, because if you want to perform like a convolution in the 3D space, different from convolutions in 2D space where you want to have dense convolutions, meaning that you have to slide your convolutional kernels over all of the, you iterate your convolutional kernels over all of the spatial positions in the 2D space. In 3D space, you could actually do it more efficiently because your input point cloud only takes a very small portion of the entire 3D volume. So you could only compute convolution there. Hence the name sparse convolution. And this convolutional scheme is actually quite easy. So we have encoder and decoder, so we could actually learn some very useful attributes. So here, what we learn is the following three things. So the first one is for each voxel, we learn the basis functions, or actually the learned coefficients that I mentioned earlier. So actually, to answer your question, it's all about you pass through your input point clouds through a UNet, and this UNet is going to tell you what is the learned coefficients of the basis functions. And the second thing is, of course, for each of the voxels, because we want to solve for the Poisson equation, you want to know what is the input data to that Poisson equation, aka the normal data at this specific point. Also, the third thing is that for each of the input points, we also want to denoise a little bit. So we predict a target scalar, which would allow us to denoise the points by using the network to predict its real value in the final indicator field. By combining all of those information, we could utilize the functions that utilize the formulations that I have all of the in the previous slides to build and solve for like this L alpha equals D linear system to minimize the surface fitting error, which would just minimize the energy function that I mentioned earlier. So finally, we utilize the solved coefficients alpha and the basis functions to form the final output implicit field, which looks like this. So this is the entire pipeline where we kind of combine the solver aspect and also the learning aspects. The basis functions, the normals are learned from a neural network, and the coefficients are solved from a closed form linear solver. Hence, we could guarantee the solution of this linear solver have to minimize your energy function where your surface has to fit to the input points. And on the other hand, because the basis functions are learned, we introduce some inductive bias or some learned priors into this entire process. So we could effectively inject learned knowledge into it. So by training this full pipeline end-to-end in a differentiable manner, we could apply it to many different data sets. For example, like on ShapeNet, we could actually train a framework on a bunch of ShapeNet chairs. So these are the reconstructed results. And also for humans. And actually, if you look at it, it's actually quite detailed in comparison to all of the previous methods. We have these details on the faces, or on the eyes, on the nose, and also on the hands. So it's even, and because of the entire framework is in a feed-forward manner, which means that we don't need these highly costly first-order methods. And actually, this could be demonstrated in the next slide. So as you can see, in this room geometry, where we have a lot of appliances or sofas, for a traditional method like ConvoNet or Siren, if you guys are familiar with the Siren framework, which tries to minimize the which also tries to minimize the energy function, but it tries to tackle it in a first order way, which means that it uses an SGD optimizer or ATOM optimizer to optimize a neural field. But that optimization is going to take you very, very long time, like 60 minutes without a very highly efficient implementation. But in our framework, all of these could be solved just in seconds because it is just a very simple feed-forward pass of a linear solve. It has nothing to do with all of these first-order gradients updates. So, and also the other good attribute of using sparse convolution is that the final linear system that we constructed is also sparse, which means that we could solve it and do the feed-forward pass, both the feed-forward pass and also the solver in a very, very efficient manner. So we could reconstruct scenes like these very large-scale driving scenes. So here is a very important, or I would consider very interesting ablation study that ablates the effects of the interpolation term. So if you remember, the energy function that we want to minimize is composed of two different components. So one is normal constraints and the other is positional constraints. So the normal constraints more or less is directly learned from the network because the n here, the normal here is inferred. While on the other hand, the positional constraints directly comes from the input point clouds. So here P is the input positions of the within the point cloud. And we could find out that all of these benchmarks, the more, the larger lambda we have, the better accuracy it could achieve, which means that by incorporating these explicit positional constraints of this point cloud, we could improve the accuracy of surface reconstruction by a large margin. And I would consider this a very interesting experiment that basically demonstrates that it's useful to incorporate these linear solvers into your reconstruction process. So the second example is actually a direct extension of the previous work. We called it neural kernel surface reconstruction, and this has already been published in CVPR this year. And yeah, we have been also doing follow-ups, but this is the most recent work that we get it published. So similar to what I have said before, we want to combine the best of the two worlds that utilizes these data-driven priora and also this accurate fitting solver. There's actually another line of work which actually utilizes the kernel method, which is the neural kernel field. It also tries to combine data-driven priora but accurate fitting solver. What they found is that so first of all, the surface is actually no longer parameterized using the linear combination of basis functions, but instead it is actually a kernel machine. So by saying this is a kernel machine, the kernel field is actually learned using the neural networks. So the kernel here resembles the basis functions that we talked about before. The kernel coefficients, which is somehow resembles the basis, the scale of the basis functions. This is actually solved via a kernel-rich regression, and this is something that is like a technique which is quite similar to the Poisson solver, but in a sense it's actually different. This is actually a kernel-rich regression, which minimizes your RKHS norm, which is short for reproducing kernel Hilbert space norm. And in that paper, in the neural kernel field paper, they also find out that the results are very accurate and also reaches state-of-the-art generalization. But the problem of that paper is that it really struggles with noise. So if your input is very noisy, and your and for example, the number of points in your input points is very large, then you could not reconstruct them very, very effectively. So this is a problem. Hence, we want to try to incorporate the sparsity, the advantages of sparsity in the previous work, it's the neural galaxy solver work, to the neural kernel field paper, and hence we have the neural kernel surface reconstruction work. So this is by far a very fast, scalable, and robust surface reconstruction algorithm, which reaches state-of-the-art performance. We also made the source code public available, so just feel free to try out on your own point cloud. Oops, sorry, the animation is a little bit messy here, but okay. So there you go. So for kernel methods, here's also another some background on the kernel methods. So the 3D representation different from the summation of basis function. So here it's also an implicit function, but it's actually the summation of these k functions, which is actually the kernel functions. If you basically constrain the functions to be equal to some values, let's say you want the positions at xj prime here to be equal to yj, then basically what you can do is to solve a kernel ridge regression problem. And the inductive bias of the implicit function, so the inductive bias here just means that how would the function perform where there are no data constraints, how you would interpolate the input points. So this inductive bias is controlled by the kernels instead of the basis functions. And we actually could also learn these prior. We could learn kernels using the neural networks. The key contribution of NKSR is actually twofold. As I've just said, that we want to utilize the sparse convolution network and also the sparse solver to accelerate the entire algorithm stack. And in order to add this sparsity into the kernel method, we actually try to choose a kernel that is limited supported, which means that the domain of the kernel, the supported domain of the kernel, is actually very small, so that the interactions between the kernels could only be limited to nearby voxels. You don't have to maintain a very, very long-range correlation, but instead you only have to maintain these near-range correlations, where we have these very highly efficient solvers. Here's an example. So previously, we have a infinite domain kernels, and we multiply it with a mask function, so you could efficiently limit the domain of the kernel functions. Also, we utilize this multi-scale attributes, which means that we have kernels of different scales, so we could cover the geometries at different scales. Like we have larger blobs and also smaller details. We want to capture both of them very well. The second thing is that we no longer, previously in NKF, in neural kernel field, we only have these positional constraints, but now we have normal constraints. This actually, if you ever work on like this surface reconstruction from point clouds, you will understand that the normal information is quite important here. From a noisy point cloud, if we could obtain some smooth normal signals, then your reconstruction could be much more smoother. So here we actually tackle the noise robustness issue by using a novel gradient-based kernel formulation. So here is the entire pipeline. It just looks very similar to the neural galaxy paper. So I'm just going to reiterate here. But most of the things, they kind of share the same spirit. The only thing changed here is we changed from the basis function, we changed from the Poisson formulation to the kernel formulation, where we could have much more flexible basis functions. So given the input points, we feed it through the sparse convolutional networks. And in the decoder branch, here what we utilize is a brand new adaptive sparse voxel. It's a structure prediction branch where we iteratively do classification of voxels and upsampling of the voxels so that the network could predict a sparse structure of the output domain. And then we fit it into a fixed sparse linear solver and combine the basis functions and the solver to form the final implicit field. Then we could extract meshes from it using dual contouring or marching cubes. We actually explore a little bit more in this work by specifically tackling the autonomous vehicle driving scenes. We try to, because in a typical driving scene, your scene geometry is usually obtained by LiDAR, and we customize our supervision to be specific to these LiDAR input, because you have this notion of the regions where you have supervision, don't have supervision, and also have ambiguous supervision. So we distinguish between that, and also in the masking module, what we have is we use an additional MLP to predict whether a region should be masked or should not, because the final implicit function we model is more or less similar to the SDF function, where a surface is usually closed. You cannot model open surfaces. But in this work, we add additional MLP branch so that you could crop away all of the regions that are excessive. The entire kernel formulation could be applied to many more attributes like colors or outlier probabilities. And in fact, the entire framework could be used in many other tasks, which we have been exploring right now, like super resolution, dynamic registration, non-rigid registration. I mean, there are tons of possibilities for for you guys to explore. So the overall results we tested on object level data sets, like ABC, Authentic 10K. We have a kitchen. We also, the code that we release contain a kitchen sink model that is trained on a mixture of various data sets, including ShapeNet, Matterport, and also color. So we demonstrate that our framework could absorb information from all of these different data sets and thus have a much more generalized version of the model. So it could be applied to most of the surfaces that we tackle. Here are some animations. As you can see, the input contains a bunch of noisy points. So the state-of-the-art POCO is actually quite slow during running, so you would actually wait for a long time before a surface could be extracted. But here we could generate all of these surfaces in a very fast manner. We tested generalization because we test generalization by sampling the training and testing set from different geometric distributions, which means that we could train on ShapeNet and test directly on room level data set. Because these two are very different geometric distributions. And it turns out, because we have a closed form linear solver here, the solver part could actually could somehow bridge or bring closer the domain gap between two different data sets, because it's closed form. There's no learning involved. It's just a solution of a linear solve, and it gives you coefficients. So it could have better generalizability. For scalability, we tested on these AV scenes using color simulator, which is also the part that I love most. We could generalize to real world outdoor data that has never been seen, like this Waymo data set. We have also tested internally with many of the NVIDIA AV data sets, and it all works pretty much pretty good on these outdoor scenes. We have we generate the data set using the color simulator, which is a great simulator, by the way. So we could have ground truth supervisions from the simulators, and also we could have a bunch of annotations and benchmarks from that. We could control the traffic and then generate the sequence of LiDAR frames very easily. We tested this on the Laguna Seca track, which is the because NVIDIA, we are also doing many researches related to AV, and also we have teams that are directly tackling these AV data and also autonomous vehicle driving systems. We have these reconstructions directly coming from NKSR, where there are 370 milliamp points, but it could be reconstructed in a very fast manner. It's under 2 minutes distributed on a small GPU cluster. And we could reconstruct both geometry and also the textures, the colors on the vertices. So you could test NKSR on your own data from today by directly pip install it and then follow all of the instructions. Like it's just a few lines of code. You can convert your input points into meshes. It's actually very easy. So in conclusion, so this neural kernel surface reconstruction is an accurate and scalable state-of-the-art reconstruction algorithm, which tries to bridge the gap between the accuracy of, or maybe bridge the gap between the inaccuracy of network feed-forward based network inference, and also the non-solver fitting based, or the non-learned solver fitting scheme. So it would just bridge the gaps using these solver-based surface reconstruction framework. And in the future, I think in the field of surface reconstruction, it is just worth exploring what are the other ways to combine the best of two worlds. I mean, for feed-forward networks, you have the ability to do, for example, completion, and you have the notion of the entire geometry, like this is the car, this is the table, you have the semantics, and thus you can complete it, and you can make the reconstruction much smoother by disregarding some of the noise in your input. While on the other hand, in some of the other frameworks like this Poisson surface reconstruction, where you have a linear solver, or for example, NUS or NERF, these first order optimization-based methods, these are very accurate and they have the guarantee of fitting the entire surface to the input points by minimizing an energy problem. It is guaranteed to reach some of the local minimum because you're constantly optimizing. And how to combine the best of the two worlds, I think there are still a long way to go on, like how to best utilize this solver-based framework. And also we want to support more surface attributes such as materials. We want to explore more extractive kernel methods. And also we want to try to even improve the speed of the current model, like even more. We want to do very, very large scale 3D reconstructions. On the other hand, on the research side, this entire framework, like I said before, it could be applied to many other tasks. It's just feel free to imagine other applications other than surface reconstruction using this framework. And I believe that in the future there could be many more applications being supported by such a framework. So that's basically all I want to say today. It's